Hello, everyone. I'm Selma from ABEEólica. I'm from the communication department of ABEEólica, and in the name of everyone at ABEEólica, I would like to welcome everyone to this webinar. Today, we have a very special webinar, and this is a very technical discussion. We will be recording it, and it's going to be on our YouTube as well. So feel free to share. We are going to send everyone the link to all our members. Okay, so to start, I'd like to ask Bruno from USP to explain what we are going to see and the objective of this webinar. Please, Bruno. And I like one other thing that I forgot. Please keep your microphones muted. We will have a 45-minute presentation, and then after that we will have time for everyone to ask their questions without a problem. Okay, so that's a message, so we can have a good sound quality during the whole webinar. Bruno, please.
Thanks very much, Selma. It's a pleasure to be here. Thanks, ABEEólica, for this opportunity. So here we are going to showcase a bit of our project. It's an international collaboration between institutions, academic institutions, and also industry from Europe and from Brazil. So today we are going to have presentations. It's a 45-minute presentations, but with the participation from the main coordinator of the project, who is Sherry Mao from the University of Nottingham, and then Jake Badger from DTU is going to follow. And then I'm going to present some slides myself, and we close with Gil from Vortex, one of our industrial partners. And then Sherry will come back to close the presentation, to do a wrap up, and then we open for questions. So thanks everyone for being here. I now hand over to Sherry, who's going to give you an introduction about the project. Thanks.
Sherry, before you start your presentation, I would like to give a tip to everyone, because you have the opportunity to rename yourselves, and it would be good for us to understand the companies that are listening to this webinar. I know that VEG has its name here, Diego from VEG, Gregory from VEG. So if everyone could rename themselves, putting the name of the company, it's really easy. Just go in your name, click with the mouse, and then rename yourselves, putting the name of the company. We appreciate that, so we could know the companies that are here. Okay, so okay, let's start. Sherry, to you.
Thank you very much. Can you see my screen?
Yes, perfect.
Okay, very nice, thanks. So good afternoon and good evening, everyone. I'm Sherry Mao from the University of Nottingham. I'm the coordinator of this transatlantic project called High Performance Computing of Wind Energy. I will firstly give an overview of this project, our work packages, our partners, our objectives, and so forth. So this project is in response to an H2020 call in 2018. The duration is exactly 2 years, and we have the opportunity to extend it for maybe half a year due to the impact of COVID. We started in the last summer, therefore it would finish around the end of next year. The contribution of EU to this project is around 2 million euros, and we have match funding from Brazilian research councils. So here is a list of our project partners. You can see that we have University of Nottingham, University of Stuttgart, Empirical College London, Technical University of Denmark, EDF, University of Twente, University of Edinburgh, Vortex, University of São Paulo, Unicamp, and Federal University of Santa Catarina. So totally, we have 8 partners from Europe and 3 from Brazil. You can say this is a mixture of universities, wind energy companies, and high performance computing hosters like HPC centers. So here is a structure of the project. In the big box, we have 3 technical work packages. In work package 1, WP1, we develop novel algorithms for wind energy simulation towards exascale. So this was led by University of Twente. Then we implement those algorithms in work package 2, led by DTU. Then we test our algorithm and our code for validations and apply them to 3 use cases in work package 3, which is led by Vortex and co-led by University of Federation University of Santa Catarina. And we have 2 supporting work packages. In work package 4, led by University of Stuttgart, we disseminate the work and exploit our results. And work package 5 is on management. You can see that for each work package, we have a Europe leader and a Brazilian co-leader. So because this is a HPC HPC project, we have to have some pilot programs. So you can see that most of them are open source parallel codes with potential towards exascale simulations. So here I listed most of them. We have U20 LES, which is for the wind farm scale simulations of wind flow passing through a whole wind farm. Then we have Nectar++ and Sharpie to simulate the interaction of wind and the oscillation of a turbine blade. So this is at the turbine blade scale. It is managed by Imperial College London. Then we have N3D managed by University of Nottingham. This is used to reduce data for wind energy simulations. We know that in wind energy, high performance computings, there are a lot of data generated. So we hope to find some method to reduce the size of data. Then we have EWP WOLF managed by DTU. So this is a mesoscale code incorporated with an explicit wake parameterization scheme. Apparently, it enables the joint simulation of mesoscale weather simulation and wind farm considerations. Then we have code Cytune, which is managed by DTU, which is managed by EDF. So this is used for microscale fluid simulations and in combination with mesoscale simulations. So here we want to combine the very large scale, for example, 1,000 kilometer simulation with a wind farm simulation. So here apparently we have, we go across a large range of problems. So there is a scale integration. And then we have Vortex WOLF LES. So this is managed apparently by Vortex. It has functions for both mesoscale WOLF simulation and large IDU simulation. We also use some other codes which are not listed as the pilot code, such as OpenFOAM, Wink 3D, Incompact 3D. So all those codes, you can say that covers from wind turbine blade scale to mesoscale. So it ranges from turbine blade to wind farm to mesoscale weather scale. Then apart from the pilot codes, we have 3 pilot applications. We call them the use cases. The first one is a wind turbine model. So this is used to test our code like U20 LES, Nectar++, Sharpie, and N3D. Then we have a Brazilian coastal wind farm site. So this will be used to test EWP WOLF, called Cytune, Vortex, WOLF LES. Then we have an onshore wind farm site in Portugal. It will be used to test something similar, like the scale integration between mesoscale and microscale. So you can say that those 3 use cases covers European wind farm sites and Brazilian wind farm sites, and also a wind turbine model. So below you can find some pictures on case 2 and case 3. So here is a brief introduction of our objectives and the achievements we have reached in the first year of the project. So our first objective is to make efficient use of HPC resources in wind energy simulation. As introduced before, this includes several aspects from the simulation of flow around a wind turbine blade to the mesoscale weather simulation for wind energy for wind resource assessments. So below I have 2 examples of our capacities developed in the first year. So we have made novel algorithms, solvers, and demonstrations for flexible turbine blade in wind turbine flow. And we have high performance RES solver with advanced subgrid and wind turbine models. So those 2 aspects enables us to simulate exactly the interaction between wind and the oscillation of the turbine blade, as well as the wind development within a huge wind farm. I mean, it will help to design or to adjust the position of wind farm wind turbines in optimal layout and optimal design of wind farms. And the second objective is on accurate meso and micro scale simulations in wind energy. So here mesoscale refers to weather scale simulations. Is used to estimate what the wind resource can be over a very large area. Then we reduce it to the micro scale, which is around several kilometers within a wind farm. The examples we have developed includes the long-term WOF with wind farm parameterization tested in the North Sea and Portugal. And we also developed the quantifications of wind power uncertainty based on a numerical tool, Dakota. So here are some pictures showing the flow chart of Dakota and our wind resource assessment. Objective 3 is to improve I/O performance of all the solvers we are developing. And also we aim at reduce the size of data generated in wind farm simulations. So here are a few examples. We developed model decomposition techniques to reduce the size of data in optimization related with fluid flow in wind turbines, in wind farm flow. So here you can say that we showed by only a few modes, we can represent the key dynamics in the wake of a wind farm. So therefore, we don't have to save the total fluid flow downstream of a turbine. Only a few modes of them will be enough. And also we developed an image-based empirical wavelet transform. So this technique is borrowed from image processing, and we use it to reduce data to compress the huge data generated in wind farm simulations. Objective 4 is to build new partnerships between Europe and Brazil for the application of HPC in wind energy. So for example, we have established several new partnerships between our European European and Brazilian organizations in wind energy and in HPC technologies. Our European partners are working with Brazilian wind farm developers and studying a Brazilian wind farm site. And the European academic partners on wind resource assessments are also working with Brazilian industry partners and Brazilian academic partners. Also, the European and Brazilian partners of this project have co-organized a workshop, and we have attracted over 200 attendees. For the impact of this project, so firstly, we want to show the improved cooperation of Europe and Brazil on advanced HPC application development. So far, we have brought together 2 HPC centers, 8 institutes, and 2 industrial companies. And we promoted collaborations between EU and Brazil partners. The second main impact is to improve the sharing of information to solve societal problems with the use of advanced computing. Apparently, wind energy has strong impact on societal problems on environments. So our research have also created new jobs, particularly in consultancy in wind resource assessment. You can recognize this from the members of our consortium. The algorithm, code, experience, and the network will also benefit other applications and societal challenges. So for example, it can be immediately applied to road vehicle simulations, to tidal turbine simulations, to tidal energy, and to other forms of such as aeronautical industries. Okay, this is all. Thank you very much.
Shall I take up the next?
Sure, please.
Yes. And Selma, if you could let me know if it's visible as expected.
Yes, it's not on presentation. Yes, okay. It's okay.
Good. Thanks very much. So good afternoon, everybody. My name is Jake Badger, and I'm at DTU Wind Energy, which is the Technical University of Denmark, the Wind Energy Department. And I'm going to tell you about the HPC for Wind Resource Assessment, which is part of what Zuri was telling about, an important part of this project, looking at scales more at the meso scale and site level, which I will explain to you. So when we do resource assessment for wind energy, it's very important to get an understanding of the atmosphere. So it's very much a meteorological study and subject. And meteorology and meteorological centers around the world, weather centers, are very big users of high performance computing. Some of the biggest computers in the world are located around weather centers. And our task is to use the knowledge, the know-how around meteorology and make it applied for wind energy resource purposes. And the key part of that is this downscaling approach, where we start with large-scale data sets. You may be using these already, such as the ERA5 data set, which is a global data set, covers the world with sort of reasonable resolution, 50 kilometers or so, but it's not also for many decades, so it's got good coverage in time and space, but it's not enough to give us an accurate wind resource assessment because it doesn't have enough detail in the terrain to capture the important flow features or phenomena. So we have to do something about that, and we do this downscaling model chain. So the first step in that is to go from these global reanalysis data to the mesoscale data. Here it's a study we're doing at the moment for the for Wind Atlas for Mexico. Also, it's an interesting event because it's actually the passage of a hurricane into the Gulf of Mexico here. But you can see now this is a wind speed map changing with time. You can see that there are some locations with high winds and others with low winds. So we can see a lot more detail in the wind features with the mesoscale. But still, this isn't high enough resolution to do an accurate wind resource assessment, because we actually need to know about the location of the turbines in relation to terrain features such as ridges and lakes and changes of roughness, forests, cities, and so on. So this is an important part of this, including more and more detail to get a better idea of the resources. So this is sort of the bottom line message, that this is a downscaling step that requires a lot of high performance computing. So for example, the ECMWF, which is the European Centre for Medium Range Weather Forecasting, has acquired very, very large computers. So it's got these two XC40 systems, and altogether that gives around 8,500 teraflops. But this is actually only 1% of exascale as it's defined as 10 to the 18 flops. So, but you can see it's very, very large computer facilities. And at DTU Wind Energy, our most recent platform for HPC is called Sophia, the Sophia cluster. And here when you put it all together, the sort of theoretical teraflop limit is around 300. So we're still kind of not really at the exascale, but we need to see how our modeling approaches fitting into this sort of changing scene, and are they going to be ready in the future to move to higher and higher performance computing. Just to show you another area where resource is very important, computer resources, is with large eddy simulations, where you can begin to resolve eddies in times and scales relevant to wind turbines. Just to show you a little bit more about actually what two partners in the project here have worked on is Vortex and DTU Wind Energy have worked with this to make the Global Wind Atlas #2 and 3. So I've zoomed up on Brazil for this example. So Global Wind Atlas, DTU first launched that back in 2015, and as I said, we're now on our third version in partnership with Vortex. You can find it at that site there. But again, this is another sort of product of a downscaling model chain, which is also highly computer resource demanding. If you just look at the number of time steps involved, it's more like something like 10 million time steps involved to cover 10 years of simulations. And when you look at the micro scale, so we've got a wind climate every 250 meters around the world. So this is actually coming to about 1.5 billion points around the world. So we're talking about very large numbers and need large resources to do calculations for all these points. And then returning a bit more back to this project. So I'm going to talk about a few aspects of the wind resource assessment activities by different partners in this project, and how they'll be sort of utilized and tested in 3 different sites. So we've got test case 2, which is a very well instrumented site in Portugal, which was part of the new European Wind Atlas project. And it's a very nice data set to use, and it's been used before in previous modeling studies. So we can use that as a kind of benchmark in order to see how far are our new methods improving in both physical accuracy, but also in HPC performance metrics. And then we've got 2 new sites in Brazil. One is an offshore site located in the interesting area where ocean currents and temperature may have influence on offshore wind resource. And then we have another site inland, and I'll talk about more of those later in the later slide. But that second Brazilian site resembles a bit more the complex terrain of the Portuguese site that we have already experience with. So in this presentation, it's very short, but I want to give you a kind of taster for some of the activities. So from DTU, we've been working on the model chain, looking at how you can pass information from the mesoscale models to the microscale models in different ways. And I'll explain two advances that have been made there. Then we have EDF. The partner there has been advancing their own methodology called RAP modeling system, and they're looking at ways of improving the cluster methodology. And then Vortex is also active in this with their wind resource assessment model chain, and they're particularly interested in investigating MPAS, a new model to use instead of WRF, and doing a nice set of validation studies where comparing the 2 model performances, and then the target is to be applying the MPAS method for the Brazilian case studies. So just to tell you a bit more about this advancement in the linkage between the mesoscale and the microscale. So at DTU, we've been working on the methodology where you take the tendencies. So this is how different things are changing in time in the mesoscale model, and using that as a way to force the microscale model. And we've been doing that for a few years, and we see this project as a chance to make some advancements on that. So there are 2 things we've advanced on that within this project. One is to change the way the mesoscale model is preparing the tendency information. So in HPC, sometimes it's very important to be aware of how much input and output is going on between the computer nodes because too much output and input and output, if it's more than is necessary, is a bottleneck for the running. So we try to do this as economically as possible. So what's been implemented within this project is a way to do this tendency averaging within the execution on the computer node itself, rather than writing out all the tendencies first and then doing the averaging as a post-processing. So this has two big advantages. It reduces the I/O aspects, but it also, this averaging also gets rid of some noise features that are in the tendencies. So if when we're doing the mesoscale modeling over Perturbed, for example, we have these nested grids domains, so we go to finer resolution. But at the end, we want to pass it through to the microscale modeling. In this case, it's using Ellipsis 3D, which is a CFD code developed at DTU Wind Energy. So what this plot is showing you is the tendency information that we get out of the mesoscale model before we do when we do it the old way, the instantaneous output, which meant we had to output a lot of data, which slowed us down, but we also had this quite noisy data set. Now with the inline averaging, we get this much less noisy field, and we reduce a lot of the input and output necessary. What that means, in fact, is that we can do the calculation using 1/4 of the time compared to before, and we use 1/30th of the amount of data going out. And this frees up a lot of computer resources. We can increase the model resolution, say, for the same amount of resource, or we can increase the simulation time, or we can set up multi-model ensembles instead. So there's always these kinds of trade-offs going on when setting up modeling. So another way we're setting up different kind of modeling approaches is to use 3D tensity fields from WRF. So what that is, when we look at the mesoscale model output, this is from a 3x3 kilometer resolution grid. We can get these tendencies for all of these points. What we've done in the past is only use one point and then use that one point to give a single profile of tendencies for the microscale modeling. And this has given these results. So here we're showing the change of wind speed with height changing with time. So what we have here is the development of a low-level nocturnal jet, or a nocturnal low-level jet. So this is a feature that's quite hard to capture, and it can also have some bearing on resources and also the siting, the conditions for design at a site. So it's important to get it if it is present in nature. So here we modeled by WRF for the Cabal case, which is a nice simple case to see if the modeling is kind of working for us. And then we've got the case again using Ellipsis 3D, which is the microscale code. And here we only use one profile to be driving the microscale modeling. But with the new methodology where we actually use 81 profiles, so actually using more information from the mesoscale modeling, more of the tendency information from the mesoscale modeling, we can actually capture the low-level jet development better. So this is also an improvement in the sort of the physical modeling aspects. So this proof of concept has been underway and shown within this project, but we still need to find the best configuration of this model chain. What resolution should we be taking the mesoscale modeling at before we pass it to the microscale modeling? And then EDF have been working on their RAP model chain. So this works by doing a lot of mesoscale modeling. So this is sort of the mesoscale modeling is something now sort of quite, I would say, sort of standard in the approach, and you can run it quite efficiently on clusters. But what's now the problem is to this downscaling, it's actually very computer demanding to do the microscale modeling. So the RAP method is to find out from the mesoscale modeling what are the different types of meteorological situation, and can they be somehow reduced to a smaller set of situations that are then modeled at the microscale modeling. So this is what this clustering step here is. It's this A and B, this is like all of the cases in the meteorology, but you can actually sort of cluster it into 4 different kinds of situation that then can be modeled in your microscale modeling. And EDF are doing the CFD simulations using the code Saturn, which is what they're using in-house a great deal for their purpose. So this project will allow them to make advancements in their approach. And here, important thing they want to investigate is 2 different ways of making the clustering analysis. So there are k-means, which is an approach where you can find out how should those clusters be formed. And then there's another method called self-organizing maps, SOMs, which is a neural network type approach, where you can create, sort of through some iterations, you create these maps of the meteorological situation, which then give you a limited set of situations that you then model with the microscale modeling. And yeah, thank you to Clementine Le Guic from EDF for providing this this slide and data. And then we've got Vortex doing work with MPAS, so testing and validating it. And this is a contribution from Vortex. So the MPAS, that stands for Model for Prediction Across Scales, and it's a community model from Los Alamos labs, and also from NCAR, but also other contributors in the community. So this is a big model with a lot of community contribution, and it's in the public domain. And it's sort of looking like maybe it's the next thing that will be used after WRF. But what's WRF? Just to say a bit more about that. WRF is being used a great deal by the wind energy community. We're using it here at DTU and many others. And WRF stands for the Weather Research and Forecasting Model, also a community model, also with NCAR very much involved. And there are many things that are sort of common between them, some of the approaches within them. The major differences between the two is that WRF has this grid, which is sort of regular, and in order to get down to smaller scales, you have to have modeling domains that are nested. So you sort of, in a discrete way, go from one resolution to another resolution to another resolution in domains that are becoming ever smaller. But in the MPAS method, you have a mesh around the globe, which is irregular, and you can have a changing resolution as you go to your region of interest, which is what the modeler decides. So how can this be used in wind resources? And that's what Vortex is putting a lot of attention to. It has some advantages in that you don't have this very discrete boundary between 2 different resolutions in the modeling system. And it may also be able to allow better feedback, both from going down in scales, but also up in scales, upscaling. And thank you to Marta Gil Biada for providing these graphics from Vortex. And she's been doing a lot of assessment of these of the MPAS for a number of sites around the world, and finding how good is this model compared to WRF, both in terms of its physical sort of accuracy, being able to capture the wind climates, both in terms of bias and mean absolute bias, but also in terms of correlation, how the variability of the winds are captured in the 2 different modeling approaches. And this is important work to see how will MPAS be suited for wind energy purposes in the future. And we're also doing collaboration with Brazilian partners in connection to the case 3 case studies. So we've got sort of a 3A and a 3B case study. What 3A is this coastal site southeast of Brazil in Santa Catarina, and this is in collaboration with UFSC, and there's a LiDAR there, and we're hoping to be able to do modeling and then compare it with the LiDAR data using a number of model chain approaches from the partners I've described. And then there's another site, 3B, case study 3B, complex terrain site for a real wind farm project inland in Bahia, in partnership with Casa dos Ventos. And we also have collaboration with the EPCC, so it's the Edinburgh Parallel Computing Centre at the University of Edinburgh. And here we're able to run the models on different kinds of platforms that EPCC have to understand how the hardware and the hardware architecture can influence the choices you make in the modeling, and also call on their expertise, and also some profiling tools that can tell us where the bottlenecks in the different programs and models exist. Now, that's my final slide. If you want to know more about these different studies, you can go to that link there where you can see longer presentations of the different partners talking about the things I've kind of gone over quite fast. And I'd like to say thank you to Vortex, EDF, and my own colleagues for providing these materials. Thank you.
Thank you, Jake.
Stop sharing.
Okay, thank you. So good afternoon, everyone. Again, I'm Bruno Souza Carmo, assistant professor at the University of São Paulo, also one of the members of this nice project. So I'm going to talk about some of the work that we have been carrying out here in São Paulo in collaboration with our Brazilian and European partners. So most of the results that I'm going to show here were produced by my team here, Rodolfo Cosipuraca, Lucas Franceschini, Marielle de Oliveira, and Daniel Francisconi de Oliveira. Okay, so my focus here will be more on the micro scale. So I'm going to talk about CFD simulations of the flow through the NREL 5 megawatts. So that's the turbine that we took as the example to test our HPC capabilities. And then I'm going to talk about blade resolved and actuator line simulations. Okay, so I'm going to show some results of the blade resolved simulations. All of them are using OpenFOAM and Reynolds average Navier-Stokes equations. So there are some simulations regarding the rotor only, and some simulations regarding the entire turbine. And then I'm going to talk about two other fronts that uses actuator line simulations, one using OpenFOAM and another suite that's built on the top of OpenFOAM that's called Turbine Foam. And also another code that's fairly new, which is called Wink 3D, which was developed at Imperial College London, one of our collaborators here. And I will close talking about ongoing collaborations within this project with our European partners. Okay, so starting with the blade resolved simulations, we use different solvers here. I'm not going to go into very technical detail here. I'm just mentioning that we have done a lot of mesh studies, and we found a compromise of using runs for the time being, although we want to go further to DES in the future. But so far we have been using K-omega SST model to model the NREL 5 megawatts wind turbine. So the two cases that I'm going to show you results from are only the rotor with a uniform inflow, 10 meters per second, and the complete turbine with a sheared inflow, typical from atmospheric boundary layer. Okay, starting with the rotor only, we have a very dense mesh here, 15 million cells, with a sliding disk approach using the AMI, arbitrary mesh interface, to deal with the motion of the rotor inside the fixed domain. So those are some results that we've got. So we were able to run 40 seconds of the blade resolved simulations, which is quite a lot because we have to resolve the very fine scales close to the blade and the largest scales in the wake. Okay, so we go from the millimeter scale to the hundreds of meter scale. So it's a very challenging simulation. And here we see some results that were obtained by Rodolfo and Marielle, students of mine. And we see very clearly the development of the wake, and in the future we're gonna study how this interferes with other wind turbines in the wind farm. Okay, those are other vorticity contours showing all the complexity of the wake that we expected just downstream of the wind turbine, and also some comparisons with results from fast code. So this is kind of the benchmark when we were talking about wind turbine simulations. It uses a very much simpler method, but it's very reliable in terms of being validated against experimental data. So we see that the results are very close. The power is almost spot on, and torus is a little bit lower than the result from fast, but less than 1%. So we are very happy with the results. Okay, talking about the turbine simulations. Now we are modeling also the nacelle and the tower. Okay, so the mesh is more complex and larger as well, 20 million cells. And here you see that the wake behind the wind turbine is very complex. So you see that's a very complex profile in terms of the average velocity, measured in different positions, 50 meters downstream, 100 meters downstream, 150 meters downstream. And you see that it lasts for quite a long distance. Okay? We took into account the ground roughness, and for these results here, 36 seconds were simulated so far. Okay? So those are the results of those simulations. The wake, again, is very complex, and the tower adds a lot to the complexity of the wind structures, as you can see here. The results are quite good as well. They agree quite closely to the fast simulations, but now we have a lot of complexity in the simulations. And since our rotor simulations agree well with fast, I think that's an evidence that the more complexity that CFD is able to capture here would be contributing to this difference, and but we are very confident of the quality of those results. Okay, now talking about actuator line simulations, that's an approach that allows us to run more turbines with a lower cost. So if you want to run blade resolved simulations with more turbines, the cost of the simulations increase a lot. And if you are interested more on the wake, what happens very close to the blade is not that important. So the actuator line is a very popular approach for that. Okay, so I'm going to show you two sets of results, one with turbines form. That's a wind turbine with no feedback controller. So we have a fixed tip speed ratio, and represent the hub and tower by actuator points. So that since we are using actuator line, but that doesn't mean that we're not taking into account the tower and the hub, because we also put actuator lines to represent those structures here. And this code has shown very good scalability, and we are using less. Okay, so it's a higher fidelity model when we compare to runs. So that's another advantage of using actuator line model instead of blade resolved simulations. Okay, so those are one of the first results that we got with a mesh that's 2.8 million points, so considerably smaller than that we are using for blade resolved simulations. And also it was much cheaper to get results from. Okay, so with that we were able to get results with just one node, while for the other simulations, the blade resolved, we had to use 10 nodes. And the results in terms of power coefficient and thrust coefficient were quite good as well. Some results of the mesh resolution requirements. Here you see that with 2.8 million points, the definition of the wake is not that good, but once we go to 9.5 million points and also decrease the time step, then you get a much better resolution of the wake features. And I end up showing this very nice animation done by Danielle, which shows the isosurface of vorticity. So we are able to capture very complex phenomena here in terms of turbulence and wake instabilities. In terms of the results in power and thrust coefficients, the power is quite good. The thrust we still have to improve a little bit, but we are in the right direction in terms of the quality of the results and also the computational performance. Now I'm going to talk about some actuator line simulations that we have performed with Wink3D, which is a very nice code that uses Cartesian structured mesh, employs high order finite difference, and also large edge simulation with actuator line method. So in terms of the representation of the physics, is very similar to turbines form, but some tests have shown that it's faster than turbines form, and it's easier to deal with as well. So for that, we employed this code to simulate a moving turbine. Why moving turbine? Here we are interested on floating offshore wind turbines. So we have simulated prescribed motion in terms of heave, so up and down, and surge, so back and forth. Okay. So this motion of the platform and the turbine consequently can modify the structure of the wake, and then that could favor turbulent structures that could shorten the wake. That's very interesting when you are thinking about a floating wind farm in the sea. Okay, so I will start showing the Perturbed Solution. So that's an actuator line simulation as well. We have uniform inflow, not turbulent, and just a rotor here. So we are interested in the features of the wake. So you see that the wake is very stable apart from this initial blob of turbulence here. But as soon as it gets out of the domain, you see that the water structure is very well defined. Have some perturbations for the outflow condition here because of the finitude of the domain, but apart from that, the wake is very stable. If we move the turbine back and forth, so that's the surge motion, 1% of the rotor diameter. So that's typical. We have performed some simulations using OpenFAS of the NREL 5 megawatts mounted on top of the OC4 platform. And that's typical of the, and using sea conditions from the Brazilian coast. And that's the order of magnitude that we see of the amplitude of motion and also the frequency of the motion. So we see that there are much more, many more instabilities on the wake here, and the wake dissipates much faster. Okay, that's very interesting for putting one turbine close to the other. We see a similar behavior when you have heave motion, so the turbine is going up and down. The instability is not that evident at first, but then very soon we see that the vortices are pairing, and the wake becomes much very diffuse, very close to the turbine. So this motion is also beneficial to the wake being dissipated sooner than it was for a fixed turbine. So that's another very interesting characteristic for the floating offshore wind turbine. But then we have to ask ourselves if this kind of motion hinders the performance of the turbine itself. Okay? So if we plot the power and thrust of the turbine and compare the stationary, the heave, and the surge motion, we see that the turbine itself doesn't suffer a lot in terms of the mean power. Okay, the results are practically the same. Of course, for the surge, since you have the back and forth motion, we see that's an oscillation of the power produced, and also the thrust. But I mean, that's by far not something that would be important in terms of the energy production. So that's a very encouraging result for floating offshore wind turbines. Okay, so I've finished by talking about our ongoing collaborations within the project. So we have some blade resolved simulations collaboration going on with Imperial College, focusing mainly on elasticity, and but bearing in mind issues like computational performance. So we are using different codes and comparing also different physics models, so we can have an idea of the impact in fidelity. And about the actuator line simulations, the collaboration is wider. So we are working together with Stuttgart 20 Imperial College, and we are studying different things here: the atmospheric boundary layer dynamics, working with non-neutral atmospheric boundary layer, for example, air elasticity and platform motion, as I showed you just now, and also how we model the actuator line inside the code. So the source term formulation, we have some ideas here about how to make it more efficient. Okay. So with that, I close my presentation and I hand over to Gil.
Okay, hello everyone. Bom dia todo mundo. I'm gonna share a few slides. I will make it shorter so you have more time to ask questions from what you have seen today. And so I'm gonna skip some of my slides just to go directly. Can you see my slides? Just to be sure.
Yes, we can.
Yeah, so my name is Julius Cano. I'm working in Vortex. I take part of this project, and I'm from a private company, which is our focus is providing wind resource information based on a very complex modeling stream using a mesoscale model called WRF. You are in the private sector, you probably have come across our data, but basically what you see is the output of a very complex process that thanks to the access to some certain level of supercomputing and an automatization system we are able to produce. But behind the stage, there is a very complex modeling system, which is very similar to what, or very similar or is on the same kind of family what Jake showed before. And this project that we are sharing with you here, this European Brazilian collaboration project, where wind industry and wind energy applications meet the high performance computing facilities. What we're trying to do with this project is to see how a new generation of high fidelity models with more computing power can help at the end the users from not only from the academia and the research. Also, the code we are using are very important to answer questions that we have at more scientific level, but also to help shaping the future of the wind resource and turbine design using the latest technology potential, and shaping this future to help, for instance, your work. And your work is basically having to deal with wind conditions, wind resource assessment, long-term analysis, site suitabilities for a specific project. So our target is at the end, when we are working with a project, to get the best information. So we are sure that the analysis, especially the energy analysis that we are conducting, are the less uncertain, they have the less bias, are the most robust. And so when we handle this information to a consultant that needs to do a due diligence, we know that we are not going to be penalized because there is a lack of information, of the quality of information. So wind energy is becoming a technology that is getting more and more sophisticated. It hasn't stopped to develop over the last 10, 20 years. When we thought that the wind turbines couldn't be bigger, they become even bigger. And so now a wind farm is a very sophisticated system that where when we want to analyze, understand what are the conditions on where these machines are going to operate, we need more information that probably we needed a few years ago. So we need to have a much more better representation of the shear, of the turbulence, of the stream events, and this means to deal with multiple modeling change. So going directly to the questions that I would like to share with you for the discussions is what the HPC, the high performance computing, can bring to the wind industry is to help us reducing the uncertainty, because by reducing the uncertainty, we get much more robust analysis, estimations of the wind energy that the wind farm is going to produce. So we have much more chances to have a higher return on the investment you're going to do. On which, but this return on investment or this reduction on uncertainty can be seen from different perspectives, basically by improving the prediction of energy, by having better spatial and vertical extrapolation using these models that, for instance, Jake presented. With this model change, get better time series that represent the long-term variability on the wind conditions. Today, we are mostly using data that are based on models to do the long-term adjustment. And also very important, the wake losses. With this new machine, with big rotors, we see that the losses from the wakes are really, really critical. And along with with energy predictions, we have also to be sure that the wind farms and the turbines and the layout that we have designed for each project is the best, and this and being the best is the one that takes into consideration extreme situations, how are the profiles and the shears and the turbulence and the conditions that are specific of each wind turbine position. And on another level, thinking in large scale integration of wind energy is very important, that we're able to optimize the energy integration. And for that, translating the wind resource approach to a time series approach, thanks to the use of time series model from the different modeling chains that we present that are able to generate answers at the wind turbine level, we will be able to really have more tools to understand how energy is going to, at the end, being sent to the network. So I'm thinking more in the Brazilian context. The key challenges that we have when we try to model the wind conditions of a wind farm in Brazil is not only applicable to Brazil, but in Brazil it's clear that the wind farm development is based on very large wind farm, even clusters. So the shadowing between these wind farms is important when we think in the future development in regions where you will, in the next year, you will have different wind farms very close one to the others. Again, the coastal sites and complex terrains is also part of the reality in Brazil. So this is a very critical aspects in wind conditions modeling. And in terms of site suitability, it's very important to start understanding which is the best, which is the real turbine performance on the project that have been built, and for that having a realistic representation of the wind condition is always a key element. So what are the challenges that the high performance computing and the wind industry have? Basically for me, and these are questions that I would like to share with you, is how to make operational the use of the high performance computing resources, and how to make it this simple as possible so it can be customizable. So it's not just that we want to run very the flagship simulations, but we want at the end that this software and this code are being used by everyone. So it's, or by everyone, it can be used for every project. So this is something that is very important in the question that we need to address with this project, is how to translate this case study that here we are developing here into something that could be employed for more general application. And this is obviously one of the role of project like this one, is to spin off this new project, new code and new methodologies to at the end become something that is much more general. And final question, how to make this high performance and high fidelity code to be cost effective, because at the end you need to have these tools accessible not just for one single run, but for all your projects. So I had more things to tell you, but just skip it because I think I wanted to go directly to the main questions that I wanted to share with you. And with this, we can go to the question that you might have from any of us. Thank you very much.
Cherie, do you have the final comments from the presentation? Should we just go quickly?
Yeah, just 1 second. Hello, everyone. Thanks for staying. I will make the final remark short. So in the second year of the project, we will focus on developing codes towards exascale simulations, and we will release our solvers, the benchmark data, examples with tutorials, and recommendations based on our 3 use cases. You may remember that the cases covers wind turbine flow, Brazilian wind farm site, and European wind farm site. So those will be released on our project website. And we will also try to establish new standards for wind simulations, particularly in wind resource assessments, such as the data fusion, and to make best use of the simulation results and the limited measurements. And we will have another workshop on HPC and wind energy in Brazil, if we are allowed to do so. Okay, so we are ready to take suggestions on the way forward. Please note that we have a few online tools. We have a project web, we have account on Twitter and LinkedIn. So if you have any questions, please feel free to ask. Okay, I'll hand it over to Bruno. If you have any.
Yeah, sure. Selma, if you want to share the question bit, please.
Well, so we finished the presentations. We now have 15 minutes for questions, but if we have more questions than 15 minutes, we can extend a little bit. There's no problem. So I'd like to know from everyone that has been listening this past 45 minutes, if someone has a question that, well, you can unmute yourself and make the question, or you can send via chat if you want to. Don't be shy. And if anyone has a question that wants to send via chat, that's okay too. While you take the time to think, if you have a question to make, I'd like to say again that this webinar has been recorded and we are going to post it on ABEEólica's YouTube in a couple of days, okay? Bruno, I don't think we have questions.
Give us just 1 minute more. So if you remember anything else after the presentation is closed, just you can contact us in the website, okay?
If you want to give an email, okay, we have a question.
Hi everyone, hi Bruno. This is Gustavo from Brazil. I'm Bruno's colleague here at the University of São Paulo. Bruno, well done. Congratulations on their interesting and also beautiful work on these simulations. I'm curious to hear from you. Have you seen people using these methods like turbines form and so on to simulate underwater tidal turbines with interaction with the free surface, or tidal turbines in very shallow environments with an interaction with the seafloor and also with the free surface of the water? Do you have this in your radar?
Yeah, we do, but so the codes that we have been using, the Wink3D and the turbines form, as far as I am aware, they haven't been used for tidal turbines interacting with the free surface, okay? So that's another level of complexity, but I know at the same time that Wink3D is the next version. Will have some free surface capability that could be used for the offshore wind turbines, but also for the underwater tidal turbines. Okay. So those tools that we are using, I'm not aware of any use, but the turbines form in principle has this capability since it's integrated within OpenForm. So it could be used for that.
Okay. We have a question here that arrived via chat from Gustavo from Total Eren. The question is, will the technological advances also be of use to short-term wind speed forecasting?
Jake, do you want to take that? Or Sherry, I don't know, one of you two guys.
Yes, I can try. So let me just see if you want to. Yeah, so I mean, in forecasting, the WRF model I was talking about has been used, is used. So anything we learn out of running that more efficiently is yeah, of benefit, I would say. Particularly maybe if it starts to include the things that aren't included by kind of standard weather centers, like for example, offshore wind farm clusters or onshore wind farms, where you might be concerned about the wake effects of that wind farm. So yeah, this would be, so it's not within this project so much, the forecasting side, but I think it is kind of readily transferable to that application.
And will the models or the files used in this project to be shared or made public?
Okay,
So,
I will address
okay.
this one. Yeah, you go, please.
Did you want me to?
Yeah, if you,
Yeah, I mean, to some extent, we got the one of the, you know, the ski, like the mesoscale model WRF is already a community model, so we would want to put back, you know, what we've learned into the community again. But that is I think it'd be more about like our practices. It would be published in papers. It's you know, it's a very large model, so it's more about how we use it that would be published rather than providing a whole new way of accessing that WRF model. With the EWP scheme, which is our explicit weight parameterization, this is something we also want to have disseminated in the public domain through the WRF repository, and that's also another sort of exercise to get that accepted. But in the meantime, then it would be our outcomes would be published in papers.
yeah, as Jake mentioned, because the size of the data is quite large, so we may not be able to share all of them. Well, for the models and the solvers, as I just mentioned, most of them are open source and they will be released with examples and tutorials. And for the earlier question on the prediction of short-term wind speed, so we are also starting to tune the mesoscale simulation by LiDAR measurements, LiDAR or mass measurements via a Gaussian process, so we can make a prediction as well as computing the uncertainty of the prediction. So the prediction and the certain uncertainty will be obtained all together. So this is actually one part of the exploitation of this project.
Okay, so Gustavo has sent her his thing. Thank you, and it's good to hear that the community will have this feedback from the project. Okay, so I think that's it. Well, Bruno has sent in our chat the link to the project. In our communications that we send to our members, we also have put the website, so you can find more information there, or you can access Bruno. He shared his LinkedIn in our chat. So feel free to do that. And I think that's it. Bruno would like to say a couple of sentences or words before we finish.
Just to thank you again, Selma, for all the help with this webinar, and thanks the audience for being here. It's very nice for us to reach to you, and we are open for collaboration, both academical and industrial. So if you think there's something that's interesting for you, for your enterprise, just come to us. There's the links for the website, LinkedIn and Twitter are there. You can reach us very easily. We are open for talks, and we are very interested in making those developments that we are doing here to really go into the society, into the industry, and really benefit the sector. Okay, so thanks very much.
Thank you too. It was our pleasure to be able to do that. I've checked here, and we have important companies listening to you. So WEG, CGN, Total Eren, CPFL Renováveis, Volbem, ABEEólica, that's a company that's starting offshore. So Camargo Schubert, we have a lot of very interesting people from the companies, and it's our pleasure to be able to make this connection between the companies and the academic. So thank you very much. Bye-bye.
Thank you. Bye.
Thank you all.